This video is about C++ move semantics. Move semantics is introduced in C++ 11. Prior to C++ 11, we can only perform copies between objects. This wasn't a big issue for plain old data structures. Copying a few integers or floats over is pretty cheap. But for slightly more complicated classes, such as containers, there could be substantial overhead when we first allocate a large chunk of memory on the heap and then copy the old data over. Move semantics is a solution to this scenario where we can save ourselves a redundant copy. We will briefly go over the copy constructor and copy assignment before we talk about the move constructor and the move assignment, alongside some C++ best practices. Let's start with an example vector class. It is simply a container that allocates an array on the heap. This is by no means a proper vector implementation, but I think it serves as a decent example for today. We have a default constructor that does not allocate any memory, and another constructor to allocate a certain amount of elements right away. Not surprisingly, we will delete the array in the destructor if the array member is not null pointer. This if statement check is actually quite significant, as we will see later, as we add move semantics to this class. Before we proceed to implement the move semantics for this vector class, let's first refine the copy semantics of the class. There is a C++ idiom called the rule of 3, which states that if any of the following 3 functions are defined, all 3 functions should be defined. And since we already defined the destructor, we should also define the copy constructor and copy assignment operators. In the copy constructor, we check if the size of the other vector is greater than 0, in which case we allocate heap memory and copy elements over in a for loop. The copy semantics we are implementing here for our vector class is known as a deep copy. We are allocating our own heap storage and copying existing elements over. A shallow copy will have 2 containers refer to the same allocation, but that is much less common for container classes. Now let's move on to implement the copy assignment operator. Since we performed a deep copy in the copy constructor, we should also be doing deep copies in the copy assignment operator. The only difference between a copy construction and copy assignment is that during copy assignment, the class instance could have been instantiated and already contains a heap allocation. Here we check if we have already allocated an array on the heap. If that's the case, we delete the array before creating a new one. Without this if statement check, we could easily have memory leaks. Now we can finally move on to an example scenario where we can benefit from move semantics. In the main function, let's define 2 vectors of integers v1 and v2. v1 is default constructed and v2 is constructed with a specified size. v2 goes out of scope earlier than v1, and before we destruct v2, we copy assign the contents of v2 into v1. If we try and run the program now, we can see that first v1 is constructed, then v2 is constructed, then we copy assign v2 into v1. This is a for loop that copies each element individually. Then v2 is destructed, then v1 is destructed. However, we can do much better with move semantics. Currently, we are copying elements inside a for loop, but since v2 is going out of scope anyways, we can actually just steal or move the heap storage from v2 into v1 to avoid the for loop iteration. The function signature of the move constructor takes a r-value reference of the class, which is this funny thing with 2 consecutive ampersands. The way I understand this is that the r-value reference is a reference to some data in mid-air that isn't assigned to a variable just yet. There is much more to the l-value, r-value, and universal references, but in this video, let's just remember that the double ampersand syntax refers to a r-value reference. The job of move semantics is to construct a class from some r-value data, and leaves the r-value in an empty state. Instead of allocating heap memory and copying elements over in a for loop, we can now directly steal the pointer address from the other data, essentially moving the data over. However, we are also responsible of leaving the r-value in an empty state. In this case, the empty state would be having a size of 0 and the pointer as null pointer. Why is this important? Remember that the R value will also be destructed. If we don't set the pointer address to null pointer right now, we will eventually delete the same address twice. This is known as a double free bug and will likely crash your program right away. I would like to emphasize that for classes with move semantics, the destructor must also handle the empty R-value object properly. Let's also implement the move assignment function while we're at it. We are basically doing the same as the move constructor by stealing the pointer address of the R-value object. But there's a catch. During move assignment, the object is already initialized and may already have heap allocations. So we should definitely check if we need to free existing heap memory before stealing pointers from the R value. It is very easy to have memory leaks when implementing something so low level even for C++. Now that we have the move constructor and move assignment ready, we are actually also satisfying another C++ idiom called the rule of 5, which states that if any of the following functions are defined, all 5 functions should be defined. However, in my own experience, I only apply the rule of 5 when I have move semantics on my classes. Otherwise, I usually go for the rule of 3 or rule of 0. Now let's go back to the example and try to make use of the move semantics we just defined. Remember that previously we are using copy semantics, which iterates in a for loop and copy elements over. We can make use of move semantics by typecasting the operand v2 into a R-value reference explicitly. However, the $& syntax typecasting is a little bit noisy, and there's actually a standardized way to do this. We can use the standard move function from C++11, which essentially does the R-value typecasting for us, but this is more standardized and it conveys your intent more clearly. If we run our program again, we can see that now we are using our move assignment operator, which directly moves the heap allocation over and does not perform any for loop iteration. In this example, it's just a container of integers, but for more complicated element types, you could imagine that we can save some measurable time by skipping the for loop copy entirely. So this is a brief introduction to C++ move semantics. It's a very fundamental part of C++ object lifetimes, and it's been over a decade, but it's still very easy to get it wrong. And of course, if you don't want to deal with move semantics just yet, you could also just explicitly delete the move constructor and move assignment operators. You would still be satisfying the rule of 5 as long as you explicitly delete them. There are also other cool stuff you could do with R-value references, such as perfect forwarding, but that's a topic for another time.